right, welcome back, everyone. So hopefully this will be the last video that I have to make, because hopefully I'll be back to teaching you guys in person on Monday, but I guess we'll see what happens at this stage. But anyways, so basically today, all we're going to do is we're going to work on doing a whole bunch of examples on how we actually use Newton's second law and the third law, etc., on how we actually solve problems. So usually when I do this in class, I would call in each and every one of you, kind of passively aggressively make you all tell me exactly what forces are acting on it, what are the components of the forces, and etc. But here, obviously, I can't do that because you're not with me at this point in time. So instead, I'm just going to kind of work through these. And then if you have any questions about these in class, just go ahead and ask. And yeah, so let's just go ahead and do as many problems as kind of humanly possible. So the first one, what I have then is what a mass, which has a massive mass M, which has a tension pulling on it, where that tension has a magnitude of 25 newtons, being pulled at an angle of 25 degrees relative to the horizontal. Now, what we're going to assume in this case is that the tension force upward in the vertical direction isn't enough to cause it to accelerate off the horizontal or off whatever surface this thing is on. So let's say there's the first surface down here. And for now, let's say that this is frictionless, so that we don't have to worry about the friction yet, so that all the acceleration will manifest itself in the horizontal direction. So in this problem, all I want to know are what, first of all, is the acceleration of my mass, and then after t is equal to 1 second, how far did it go? So let's assume that this thing starts off at the initial position of x0 equal to 0, and let's assume it starts at rest, so my initial velocity is 0. Good, so let's look at part A first. So part A, first thing we're going to do is draw our free body diagram. So when it comes to using Newton's second law, first thing we're always going to do is draw our free body diagram. So let's leave all the forces that are acting it. So we know we have the tension force. So there's my tension. We also know that there's going to be weight to it, since it has a mass. So I have to have mg pointing downward. And since it's on some sort of surface, there must be a normal force. So my normal force is going to be perpendicular to the surface. So this is my free body diagram. And again, I said it's frictionless, so there's no friction. So we don't have to worry about that guy. So in this case, I'm going to choose a coordinate system. So let's choose our coordinate system. So since the acceleration is in the horizontal direction, let me go ahead and draw that. And again, remember, as I mentioned last time, acceleration is not a force. That's why I'm not going to draw it attached to the body. I'm going to go ahead and draw my positive x direction in the direction of the acceleration. And then my y direction, I'm going to choose vertically upward. Now, in this case, I could look at the sum of the forces in both my x direction and my y direction, but since I'm only interested in the acceleration, and since there is no friction force, well, we know the friction force is proportional to the normal force. What that basically tells me is I can ignore the y direction and only look at the x direction. Let's go ahead and do that. So in this case, I'm going to say that some of the forces in the x direction. Now, here, since this thing is accelerating in the x direction, again, I would say, is it accelerating in the x direction? I would say yes. So I'm simply going to write some of the forces then is equal to the mass times the acceleration. Now, in this case, what are the forces which are acting in the x direction? Well, the only force which is acting in the x direction is if I drop my perpendicular here from the tension, then I want this portion of the tension. Now, according to this angle here, that is the adjacent side. So this is then going to be the t cosine of theta portion. So here I'm going to get t cosine of theta, that's the only force in the x direction, then is equal to the mass times the acceleration. So my acceleration then is simply t cosine of theta divided by the mass. Plug in my numbers, this is then going to be 25 newtons times then cosine of 25 degrees, all divided by 5 kilograms. Plug in my numbers, what I find in this case then is my acceleration, which happens to be 4.53 meters per second. So this is my acceleration. Great. Now, as I had mentioned in the first video, the point of doing Newton's second law, or solving Newton's laws in general, is to get the acceleration. Once I have the acceleration, which in this case is constant, I can now apply my kinematic equations to now be able to find whatever it is that I want. So in this case, since I'm looking for the distance after some time frame of delta t, then in this case, I'm going to use my second kinematic equation. So let's use our second kinematic equation. For b, we would say, using kinematic equation number 2, x is equal to x naught plus do not times t plus 1/2 the acceleration times time squared. Now here, we assume the initial position was 0. The initial velocity was also equal to 0. So this thing reduces down 1/2 the acceleration times time squared. Plugging this in, this becomes 1/2 the tension times cosine of the angle divided then by the mass times the time squared. Well, look at my numbers. What I get in this case then is this goes 2.27 meters. So this is the total distance it travels in 1 second. Good. So nice and easy. So again, the point of Newton's second law is to, again, come up with the acceleration and then use the fact that acceleration is constant to then determine what we want to know then from kinematics. But sometimes, as I mentioned earlier, we have to do it in reverse. And a good problem to look at that is problem number 2. So this one says I have a hockey puck. So here's my hockey puck. Great. This thing has some mass, which I don't know what it is, but that's irrelevant, as we'll find out later. I'm going to give this guy some initial velocity. So let's say initially I'm going to give him some velocity. Let me do that in green, v initial. Okay. This thing then is going to slide across this pond. Let's say here's my pond. And so eventually it's going to reach this location over here, where it's going to stop, which means my final velocity in this case is going to be 0. And I know it's going to travel this total amount of distance, let's call that delta x, where delta x is equal to 120 meters. Mm-hmm. So what this means is what? It starts off with initial velocity non-zero, finishes with a velocity equal to 0, which means my acceleration is going to have to be in this direction, opposite direction, which means this thing has to feel a friction force. So what I want to know in this case then is random color, purple, great. In this direction, what is then my kinetic friction, or more specifically, what I want to know in this problem then is what is the coefficient of kinetic friction of the ice? So this is what. So good. So let's use this problem here. So let's start off with the way we did it before. So meaning let's start off with a free body diagram. So again, let's label all of our forces. Well, again, I know this thing has a mass, so I have an mg down in this direction. And I have a normal force. So I have a normal force pointing upward, perpendicular to the surface. And we now know that we have a friction force. So that friction force will be in this direction. Now, at first, you may be freaking out in the fact that I haven't given you a mass, but if I don't give you a mass, the reason for that is it's going to cancel out at some stage, which means that I don't actually care what the mass happens to be because it's irrelevant for the problem which it is that I'm solving. So if you're ever looking at a homework problem or an exam problem and you see there's no mass given, don't freak out. It just means it's going to cancel at some stage, so we don't have to know. So in this case, I would then draw my free body diagram, just did that. So now we can put in a coordinate system. Now again, what I know is the acceleration is going to point in this direction, so it's slowing down. So I'm going to choose my positive x direction to be in the direction of the acceleration. So it's going to be in the negative x direction, or to the left, when we're calling it positive x direction. And again, I'm going to choose positive y to be. Good. Now, in this case, let's look at the sum of the forces in the x direction. So again, is it accelerating the x direction? The answer is yes. I'm going to write this as simply m times a. And here, the only force acting in the x direction is my kinetic friction. So I get my kinetic friction then is equal to ma. And we know by definition, the kinetic friction is the coefficient times the normal force is then equal to m times a. Right. So good. We've already found the coefficient. So let's solve for the coefficient. My coefficient then is equal to m times a divided by the normal force. So let's look at each one of these things. The mass we don't know, it's not given to us in the problem. We also don't know the acceleration at the moment, and we also don't know the normal force. So let's start getting into some things. So the first thing we can get rid of is actually the normal force. So we know the normal force will come by looking at the sum of the forces in the vertical direction. So let's look at that. So let's call that the sum of the forces in the y direction. Again, I'm going to ask myself, is it accelerating in the y direction? According to my picture, the answer to that is no. So I'm going to get simply equal to 0. Here, I have all of the normal force. So here's all my normal force pointing in the positive direction. So since that's in the same direction as positive y, that's going to give me a positive normal force. And then I have all of the weights, or the gravitational force, pointing in the y direction, but it's in the negative y direction because it's pointing opposite to the direction of positive y. So I'm going to have minus m times g then is equal to 0. Using this, I can solve for my normal force. My normal force then is simply mg. Plugging that into this problem, I can get a over g then is equal to my coefficient. Now, this would be great. I could easily find my coefficient if I know what the acceleration is. Now, in this case, I don't know the acceleration, but I can find the acceleration from doing the kinematics first. So in this case, notice that I can actually use kinematics to find the acceleration. I can do that because I know the initial velocity, where my initial velocity was. Did I write it down? No. So my initial velocity, let me write that down here, is 20 meters per second. Good. And I know the final velocity, that's simply equal to 0. And I know the displacement. So, excuse me. Using all those, what I know then is by the third kinematic equation, my final velocity squared, which is equal to 0, is equal to my initial velocity squared, minus, because the velocity and the acceleration are in the opposite direction, 2 times my acceleration times my displacement. So according to this, my acceleration then is going to be equal to the initial velocity squared divided by twice the displacement. So I'm going to go ahead and plug that in here. It's going to be equal to my initial velocity squared divided by 2 times my displacement times g. Plug in my numbers. So this is going to be 20 meters per second squared divided by 2 times 120 meters times g, which is 9.8 meters per second squared. Plug in my numbers. So first thing notice is that, remember, the coefficient has to be dimensionless, and this thing is dimensionless. On the top, I have meters squared per second squared. On the bottom, I have a meter times a meter per second squared, which is a meter squared per second squared, which is dimensionless. Or again, I can think about it as an acceleration divided by an acceleration, which is also dimensionless. So plug in my numbers. What I find in this case then is my coefficient works out to be 0.17. So this is my coefficient of kinetic friction. So not too bad. So let's do another problem. So this time, let's make it some connected objects. So let's make it a little bit more difficult. Let's look at 2 objects. So in this case, I'm going to have this. So I have an inclined plane. Here's my inclined plane, which is inclined at an angle of theta, where theta is equal to 30 degrees. I'm going to have a mass m1, where m1 is going to be on the plane, attached over a cord, which goes over a pulley to another mass of m2. So this is my scenario here. And let's put in all these things. So I know m2 is equal to 7 kilograms, and I know m1 is equal to 4 kilograms. And we're going to do this actually 2 ways. So in this problem, number 3, we're going to look at this in the frictionless case. So I'm going to say in this case, my system, or my plane in this case, is completely frictionless. So my mass m1 is allowed to slide across it without friction. Then in the next problem, we're going to do exactly the same thing, and then do it now with friction, and then talk about the differences between the 2. Excuse me, Brandon. So what I want to know in this case then is just simply, what's the acceleration? What is my acceleration of my system? Now, let's talk about this. So in this case, I didn't tell you the direction of the acceleration. So what I can do is, whenever I have a frictionless surface, especially when I have a frictionless surface, I can assume the direction at which this object is going to accelerate. Meaning I'm going to assume the direction at which m2 is going to accelerate, and we know from Newton's third law that turns out that m1 is going to accelerate with the same acceleration, at least the same magnitude of the acceleration, and then the direction just has to be consistent with what the other one is doing, meaning that they both can't be accelerating downward, because that would imply that the string is not there, and then that just wouldn't work. So if I assume that m2 accelerates downward, m1 has to go up the plane. And if I assume that m2 accelerates upward, then m1 has to go down the plane. Whichever choice I do, it turns out it doesn't matter. The only thing that's going to happen is, at the end of the day, I'm going to get a positive sign or a negative sign. Positive sign means I assumed the correct direction. And then the negative sign just means I wrongly assumed the direction. But the magnitude will still be the same, so it actually doesn't really matter. It just means I got the direction wrong. Not a big deal. So let's go ahead and talk about this. So in this case, the only way I can think about choosing my direction, instead of just arbitrarily, is look at the size of m2 versus the size of m1. In this case, I can see that m2 is significantly larger than m1, so I can safely assume that this guy's probably going to accelerate downward, and this one's probably going to accelerate upward. Now, again, I could be wrong. I'm going to get a negative sign at the end of the day if I am, but ultimately it doesn't matter. But I need to make a choice, so that way I know how to put my coordinate axes. And that choice is also there to make sure that I'm consistent and that this thing is not doing two different things, meaning that one, they're not both going downward and they're not both going upward, because neither one of those two would make sense. So as we talked about in the previous video, if I'm dealing now with connected objects, two separate objects, I'm then going to draw a free body diagram for each one of these two. But again, what's going to connect these two objects together is simply the tension. So let's start labeling. So let's look at M1 first. So M1 we know has a mass, so therefore it has to have a weight. So I have M1G downward. We know there's a tension, or there's a normal force because it's on a surface. So my normal force then is going to be off in this direction. That's going to be him. And then it also has a tension. That tension will be trying to pull it up the plane. So this is my tension T. Now let's look at, in this case, I know it's also frictionless, so I can ignore the friction force. So that's it. There's no more forces on M1. M2, I know this guy has a weight. Right? This has a mass. So again, I have M2G pointed downward. I know it has a tension force. That tension force is pulling it upward. And you can think about it as it is trying to keep it from undergoing free fall, like I mentioned in the other video. And then finally, the other question is, does this guy have a normal force? Well, the way I've drawn the picture, this one is being suspended in air, which means it's not attached to the floor, which means no, there is no normal force. Remember, normal force is a contact force or a reactionary force between two different objects. In this case, I only have one object. It's not attached to anything else. It's not being rested against anything else. So there is no normal force. Now, again, I'm going to label my accelerations just so I know the direction, so I can choose the direction of my coordinate system. Now, again, whenever I work with connected objects, I can have two different coordinate systems for each one. Doesn't matter. I don't have to use the same coordinate system. I can, but in this case, that would be annoying because now my acceleration would be in two directions instead of just one. So in this case, it's better to use a tilted coordinate system. So for M1, I'm going to choose my X up the plane, because again, that's the direction of my acceleration. Y then is going to be along the direction of a normal force, which means if I extend it downward, then the angle theta here is exactly equal to the angle of the plane. For M2, since it's accelerating downward, I'm going to take my positive Y direction to be downward. So from here, we're now going to use Newton's second law. So let's look at the sum of the forces on each one of the two objects. Let's start with M2 this time. Change it up. So in this case, I would say some of the forces in my Y direction, because the X direction is basically irrelevant. Nothing happens in the X direction. So in the Y direction, is it accelerating? The answer again is yes. So I'm going to write in M2A. Now, as I mentioned in the previous video, make sure you pay attention to your subscripts, because you can get your subscripts wrong. Or you could forget them, which then cancels out a whole bunch of masses, which just wouldn't be good. So in this case, the left-hand side, again, is our geometrical representation. Well, for this guy, I have two forces in the Y direction. I have M2G and I have my tension. In both cases, I have all of the force along that axis. So this is my weight. This is then my tension. Both of them are in the Y direction. So in this case, what I can do then is finally look at the direction of M2G versus Y. Well, that's in the same direction. So that means it has to be positive. So I get an M2G. And then my tension in this case is opposite the direction of Y. So I get a minus sign, then all equal to M2A. Good. That's it. So what this one says is I can find the acceleration if I know M2, which I do, if I know G, which I do, and if I know the tension. At the moment, I don't know the tension. Where's the tension going to come from? Well, it's going to come from the other mass. So let's look at the other mass. So let's look at M1. So again, M1, I have the choice of looking at both the sum of the forces in the X direction and the sum of the forces in the Y direction. But much what happened in the previous problem where there was no friction force in problem number one, there's also no friction force in this problem, which means I can ignore the sum of the forces in the Y direction and only look at the sum of the forces in the X direction, because that's the only place the acceleration is going to come from. So in this case, I would say some of the forces in my X direction, is it accelerating? Again, the answer is yes. I get an M1A. In this case, again, I have two forces acting in the X direction. I have this tension force, and it's all of it in the X direction. And it points in the positive X direction, so it's going to give me a plus sign. And in this case, now I have this portion now of the gravitational force, which is pointing down the plane, right? So in this case, I have only a part of the gravitational force. And since it points down the plane instead of up the plane, it's going to be a negative sign. So I'm going to get minus mg1, and then which component do I have? Do I have the sine components or do I have the cosine? again, the way I determine is I look at where the angle is relative to the magnitude of the force. So in this case, my component I want, which is the bold one that I drew here. So in this case, it's opposite to the angle, so that makes it the sine portion. So I get a minus m1g sine of theta is then equal to m1a. So let's look at this guy. So this one says, and then that's what? Again, I can find the acceleration if I know the mass m1, which I do, if I know g, which I do, if I know the angle, which I do, and if I know the tension, which again, I don't. But again, I can combine these two expressions together by noting that the left one is equation 1 and the right one is equation 2. Notice that equation 1 comes with a positive t, equation 2 comes with a negative t. So if I add these two together, the t's are simply going to cancel. So let's go ahead and do that. So now what I want to do is look at equation 1 plus equation 2. And again, when I do that, those two tensions are going to cancel. So let's look at this. So by adding those together, what I'm left with then is m2g minus m1g sine of theta is then equal to m1 plus m2 all times. From here, I'm going to solve for the acceleration. My acceleration then is going to be equal to, let's factor out a g. So I get an m2 minus m1 sine of theta, all divided then by m1 plus m2. Now, again, at this stage, it's good to get into the practice of making sure that this thing is dimensionally correct. So by looking at terms, what I see here is an acceleration on this side. So this whole term on the other side has 7 dimensions of acceleration. So I have an acceleration here. So I have acceleration is equal to acceleration times something. So this something in green here must be dimensionless. And I can see that it is because on top I have mass, on bottom I have mass. So mass divided by mass is indeed dimensionless. So good, from here I'm going to plug in my numbers. Plug in my numbers, what I find in this case then is it has an acceleration of 4.45 meters per second. So this is my acceleration when I don't have friction. So good, so let's do exactly the same problem again. Problem number 4, where again I have my inclined plane. So here's my inclined plane. Angle again of 30 degrees, mass m1, where m1 again is equal to 4 kilograms. Over here, mass m2, where m2 has a mass of 7 kilograms. Again, this guy is going to be attached to a string, which goes over a pulley. Well, that pulley then is, again, massless and frictionless. But the difference now is that I do have a coefficient along the plane, where the coefficient of kinetic friction is equal to 0.3. So basically, now what I want to do is redo the problem and see what happens to the acceleration. So all I want to know then, again, is what is the magnitude of the acceleration? As this thing now has a friction force. Now, let's think about our expectations, right? Or make some predictions. So our expectation is what? How should this new acceleration compare to the previous acceleration? Should be it accelerating the same, faster, or slower? Well, let's think about this. It can't be the same. It can't be the same because now I'm going to add in an extra force. So when I add in that extra force then is going to change what the overall acceleration is, which means it can't be the same. Can it be more? Well, in this case, it can't be more because remember the direction of the friction is always opposite to the direction of motion, which means the point of the friction force is to slow it down. So in this case, it can't be more. Can't be more. So the only option it has is that it has to be less. So in this case, what we should find is that the acceleration here is less than in the frictionless. And we'll come back to that and make sure that that's actually true. So good. So let's do the same thing just to get some practice. So I'm going to redraw my free body diagrams. Again, here's M1, and then over here is what? Now again, we know M1 has a weight to it, so it has a mass. So we have M1G downward. M2 also has a weight to it, so I might as well write that one in. So I have 2G. We know that's what's trying to pull this guy up the plane is the tension. And we know this one is trying to keep it from undergoing free fall. So that's the tension. And let's assume the direction of the accelerations are the same, which they should be, right? The friction is not going to make it accelerate in the opposite direction. We also know that the normal force stays the same on this guy. So we still have the normal force. There is no normal force on the other one because it's still not attached to the ground. But now the new piece is that this guy has a kinetic friction force, which would be parallel to the surface, which in this case means it's parallel to the plane, and it's in the opposite direction of its acceleration, so it has to be down the plane. Again, just redraw my accelerations, acceleration, acceleration. So here I'm going to use the same coordinate systems as before. Take my positive x in the direction of the acceleration, my positive y, so that this is then theta, and then positive y downward here because that's the direction of the acceleration. Same as before. Let's write out some of the forces for M2 and some of the forces for M1. Let's do M2 again, just because it's easier. Again, I would say that some of the forces in the y direction, are they accelerating? Answer is yes. Again, so I get an M2A. Same reason as before, I get an M2G minus my tension is equal to M2A, because again, I have all of M2G along the y-axis, and it's pointing in the same direction as y, so it has to be positive. Excuse me. I have all of the tension, which is in the opposite direction, which causes it to be negative. Now, for the other one, let's look at some of the forces in the x direction again. Is it accelerating AX? Answer is yes, so I'll get an M1A. So here now I actually have three forces in the y direction, or sorry, in the x direction. So I have the tension, I have all of it. I have this portion of the gravitational force again, which again is the opposite side of the angle. So this is going to be the sine portion again. So I get a minus M1G sine of theta. And then I get the tension, and I have all the tension, but it's in the negative x direction because it points in the opposite direction. Yeah, so I get minus my friction force then is equal to M1A. So here, same thing as before. This one says that what I can find the acceleration if I know M1G and the theta. The answer to all those is yes, I do know them. If I know the tension, which I don't at the moment, but I can find it by looking at what the M2, and if I know the friction force. Well, at the moment, I don't know the friction force, but I do know that the definition of the friction force is the coefficient of the friction times then the normal force. So now I'm going to use the sum of the forces in the y direction to find the normal force. So let's look at the sum of the forces in the y direction. So in the y direction, is it accelerating? The answer is no, because all my acceleration is in the x direction. So I have what? The normal force, all of it. And I also have mg, but I have now this component of mg. And since this is the adjacent side, then this portion is going to be mg cosine of theta. So in this case, I get a minus, because it's in the opposite direction as positive y, m1g cosine of theta equals 0. So solving this tells me then that's what my normal force then is equal to m1g cosine of theta. Plugging that back into my original expression using this definition now, I finally get my tension minus then m1g sine of theta minus mu sub k m1g cosine of theta is all equal to m1a. Good. From here again, now I've taken all the vector properties into account, same thing as before. So now what I'm going to do is just simply treat this as an algebraic expression, number one, algebraic expression number two. And again, I notice that's what here I have a positive tension, here I have a negative tension. So if I add those two expressions together, they're simply going to cancel. Let's go ahead and do that. So on the next slide here, let's consider equation one plus then equation two. So here I'm going to get what? An M2G, and then I get a minus M1G, and then I get a sine of theta plus mu sub k cosine of theta. So just factoring out that M1G, and all that then is equal to M1 plus M2 times A. Solving for A, when I get A then is going to be equal to, so let's bring the G out front. So I get an M2 minus M1 sine of theta plus mu sub k cosine of theta, all divided by m1 plus m2. Okay, just make sure they're dimensionless. Here I have acceleration, here I have acceleration. So everything here must be dimensionless. And again, it is because I have a mass and a mass divided by a mass and a mass. So that is dimensionless, because remember, everything else in here is dimensionless quantities. So no units, and no units. Good. Plug in my numbers. What I find in this case then is my acceleration in the frictionful case becomes then 3.53 meters per second. Oh boy. So in this case, again, going back to our expectations, we said that the acceleration here should be less than in the previous case. In the previous case, with no friction, we had the acceleration was 4.445 meters per second squared. Now with friction, we say it is 3.53. Which one is bigger? Well, the 4.45, which means that indeed the acceleration in the frictionless case is greater than the acceleration in the frictional case. So again, this makes sense. So let's do another one. So next one is what we saw in the demonstration, which is what's called an Atwood machine. So let's look at that one. 5. A good example number 5. So example number 5, what I have is a massless, frictionless pulley, which is connected now to 3 masses. So over here, I have this mass here, let's call that mass M1, connected then to another mass on this side, let's call that guy M2, which is connected by another string to another mass of then M3. Right. Let's put in some numbers. M1 here is equal to 5 kilograms. M2 is equal to 4 kilograms. And then M3 is equal to 3 kilograms. Right. Now, since I have more mass on the right-hand side than I do on the left-hand side, that means this thing is going to accelerate down in this direction, and this one accelerates this way. And again, Newton's third law basically just tells me that the acceleration of all 3 of these blocks are all the same. That's what Newton's third law tells me. So for this problem, what I want to know is, for part A, what's the acceleration of the system? I mean, what's the acceleration of each block? And then finally, for part B, what is the tension, or what are the tensions in the strings? Talk about how many strings there actually are and how many tensions we should have. So let's think about part A first. So part A, again, I'm going to look at connected objects. I'm going to draw 3 body diagrams, M1. Now, before I get all crazy on the right-hand side, let's think about M1, for example. So M1 is being pulled by the tension in the string, but does M1 care that it's being pulled by 2 different masses, M2 and M3? No, it doesn't. So the only thing M1 cares about is that it's being pulled by a total mass of M2 plus M3, not just by a single mass M2 attached to another one. By another one, M3, right? So basically, all it cares about is that it is being pulled by a net amount of mass of 7 kilograms. It doesn't care that it's 2 separate masses of M4 and M3. All it cares about is that. So what I'm going to do is, instead of looking at all 3 of these masses, I'm going to actually combine these 2 into one and then redraw my picture. So that now I'm going to have a single mass on this side of M1 and then a single mass on this side of let's call that guy M4, where M4 is simply equal to M2 plus M3. Okay. So in this case, I'm going to consider only those 2 free body diagrams. And then we'll break it up into other free body diagrams to talk about the tensions. So good. So in this case, I have the tension on him. So this is going to be tension, let's call that T1. And then on this side, it's going to be in the opposite direction of T1. But again, those 2 tensions have to be the same by the fact that it's Newton's third law, as well as the fact that the pulley is frictionless and massless. They both have a weight to it. So I get an M1G down in this direction. This one has an M4G in this direction. They both have accelerations. This one is accelerating downward, while M1 is accelerating upward. So from here, I would do the same thing. I would then write a Newton's second law for each one of these 2 different masses. So in this case, I'm going to choose for M1, positive y direction to be pointing upward, because that's the direction of the acceleration. And then I'm going to choose my positive y word to be downward on M4, because that's the direction of my acceleration. So good. So here, let's start off with M1. So I'd say that some of the forces in the y direction are, in this case, is it accelerating? The answer is yes. So this is just going to be M1 times A. So in this case, I have a tension upward, and then I have M1G downward. So since tension is upward in the same direction as positive y, that is positive. I have all of M1G downward, so that's negative because it's in the opposite direction, equal to M1A. For M4, I'm going to say the sum of the forces in y direction are equal to M4A because it is accelerating. In this case, we need to be a little bit careful because now I still have the tension T1, but T1 is in the opposite direction as positive y, so that's going to give me a negative. And then I have the M4G, but in this case, M4G is in the same direction as positive Y, which gives me a positive sign, and then equal to M4A. So notice that the left-hand sides are different by the fact that not only the masses are different, but they have different signs. They're negative of each other. So again, the M11 says I can find the acceleration if I know M1G, which I do, and if I know T1, which I don't. The other one says I can find the acceleration if I know M4, which I do, if I know G, which I do, and T1, which I don't. But again, combining these two expressions, I can then get rid of T. So I'm going to do that. I'm going to notice that, again, these are just algebraic expressions. So if I take equation 1 and equation 2, if I add them together, again, the tensions are going to cancel. So let's work with that. So I'm going to take equation 1 plus equation 2. So in this case, I'm going to get a M4G minus then an M1G is equal to M1 plus M4 times A. Which means then, solving for A then is going to be equal to G, M4 minus M1 divided by M1 plus M4. Again, just to check the dimensions are correct, I have acceleration, great. Dimensionless, good. So now I have acceleration is equal to acceleration. Right. Plug in my numbers. What I find in this case then is my acceleration works out to 1.63 meters per second. Good. So now I can go back to looking at M2 and M3 separately. So let's look at M2 and M3 separately. So M2, we already know we have a tension T1 upward in this direction. We know it has a weight, so I have M2G this way, but it's also attached to another string, by another string, which means it's being pulled down in this direction by another tension of T2. Simultaneously on T3, because it has a string attached to it, it has to feel the tension 3 upward, but since it has a mass to it, it has M3G downward. And again, we know both of these two are going to be accelerating downward. Oops, that should be it. There we go. Good. So basically what this says then is that what? Overall, I have two tensions, right? I have the tensions in each of the two strings. Now, what I can do is I can actually use this expression here, either equation 1 or equation 2, to solve for T1. Since now I know the acceleration, I can use them to solve for T1. And then I can get T2 by either looking at M2 or at M3. Now, which one do I use? Well, ultimately, it doesn't matter. It's going to give me the same T2. But typically, what we'd want to do is we're going to, where are we? We're going to then use whichever one is actually easier. So in this case, the M3 is actually easier. So let's use M3. So in this case, I'm going to use M3, choosing a positive Y direction to be downward to then find an expression for T2. So let's do that. So let's look at M3. So our M3, I would then have the sum of the forces in the Y direction are equal to, is it accelerating? Yes, I get an M3 times A. So in this case, M3G is downward in the same direction as my positive Y. So I make it positive and all of it pointing that way. T2 is upward, all of it along the Y-axis, but it's pointing in the opposite direction as positive Y, so it makes it negative M3A. So good. So according to this, this tells me that T2 then is going to be equal to M3G minus A. And then going back to, say, equation number 1, we can then solve the tension that way, and that says that T1 is going to be equal to M1G plus A. So here I get T1 is equal to M1G plus A. So pulling in my numbers, what I find in this case then is T1 works out to be 57.15 newtons, and then T2 is going to be only 25.51 newtons. Now, just before we move on, let's just make sure that makes sense. And that does make sense because, again, if I go back to my free body diagrams, tension T1 has to be greater because it's supporting all three masses, basically. So in this case, M1, it's supporting his weight, as well as the weights then from the two masses, M2 and M3. However, T2, which is the tension in this portion of the string here, this is going to be less because it really only has to support then M3. Right? So in this case, it has to be less, which indeed it is, which can make us feel happy. Good. So let's do one more example problem. And then we can meet up and talk about more things on Monday. So this is what, problem number 6, right? Yeah, 6. So problem number 6. So this says I'm going to again have two connected objects. So here's my table. My table then is going to have a pulley, which is then going to be attached to a hanging mass down here, which is going to be M2, which is 7 kilograms. And then on the table itself, I then have this mass M1, where M1 is 4 kilograms. So let's say in this case, there is a coefficient of kinetic friction across the table, where that coefficient is 0.3. Good. So in this case, again, what I want to know is simply what's the acceleration on this. So again, we have connected objects, which means, again, I'm going to start off with my free body diagrams for each of the two masses. Let's label all the forces on each mass. So in this case, M1 has a weight to it. So I have M1G downward, M2 has a mass, so I have a weight downward, M2G. I have a tension. Tension in this case is pulling M1 horizontally to the right, but it is pulling M2 upward. And again, I know they have to be in the opposite directions by Newton's third law. Right. I know I have a normal force on the one that's on the table. So there's my normal force perpendicular to the surface, opposite to the direction of the weight. And then finally, there is a kinetic friction. A kinetic friction will be in the opposite direction as the tension, causing it to slow down. So over here, I know the one on the table is going to accelerate to the right, while the one hanging is going to accelerate downward. So for the one that's on the table, M1, let's take that again, the positive x direction is in the direction of tension, positive y is upward. And then for the hanging mass, positive y will be downward. And that was good. So we're going to do the same thing. Let's look at some of the forces on M2 and M1. So for M1, we know we have a friction force. The friction force, again, is proportional to the normal force, which means, again, we have to solve for the normal force. So let's look at the sum of the forces in the y direction first. The sum of the forces in the y direction, is it accelerating in the y? The answer is no, so I get a 0. So here in the y direction, I simply have the normal force and I have the weight. I have all of those forces, all the components. So in this case, I have a positive normal force because it's in the same direction. Y minus the weight is then equal to 0, which means my normal force then is simply equal to the weight. In the x direction, we're going to have then the sum of the forces in the x direction are equal to, is it accelerating? The answer is yes. So I get an M1A. And then here we have what? All of the tension in the positive x direction. So I get a positive tension. And then we have what? The friction force, which is also all the way along the x direction, but it's in the opposite direction as the x direction. Minus friction force is then equal to M1A. So this one says I can find my acceleration if I know the friction force, which I know the new normal force now. So let's go ahead and plug that in. So I get T minus mu sub K, M1G is then equal to M1A. And if I know the tension, which I don't, where's the tension going to come from? Well, it's going to come from the other mass. So let's look at that. So let's look at the sum of the forces in the y direction. Is it accelerating in the y? Answer is yes. I get an M2A. I have the weight, all of it, in the direction of the positive y, so it's a positive sign. And then I also have the tension force, all of it. But since it's in the opposite direction, it's positive y, and that's going to give me a negative sign. So again, this one says that's what I can find the acceleration, again, if I know M2, if I know G, I know all those things, and if I know the tension, which I don't, but again, I can find the tension from the other one. Or again, I can say, well, these are two algebraic expressions. So again, one comes in with a positive sign, one comes with a negative sign. So if I add them, the t's are simply going to go away. So let's go ahead and do that. So what I get then is that's what? 1 plus 2 gives me an M2G minus then a mu sub K, M1G is then equal to M1 plus M2 times A. Solving for the acceleration, I get the acceleration then is equal to G times then M2 minus mu sub K, M1, all divided by M1 plus M2. Again, let's just double check, make sure we have dimensionally correct. Acceleration, good. That means this part shouldn't be dimensionless, which again it is, because mu sub k is dimensionless, so I've mass divided by mass, which is simply dimensionless. Plug in my numbers. What I find in this case then is this is going to accelerate at 5.17 meters per second squared. Good. So this is my acceleration for this system. Now, again, things to point out here are, again, I have to choose in the direction of the acceleration. Most of the time that's implied to me, but sometimes when it's not, like in this case and the other cases, I just have to assume a direction, but I can usually assume by physically what's happening. The problem, and I have to make sure that when I have connected objects, the two connected objects are both accelerating in the same direction. So meaning they're both doing logically what they should be doing. So again, if one is accelerating downward, this one's accelerating to the right. I can't have one accelerating downward and the other one going to the left, because that would imply the string is what, stretching, which it's not going to stretch. That was one of our assumptions. And also remember that here, notice that when I'm doing with connected objects, I never make direct reference to the other object when I'm looking at the sum of the forces. I'm only considering the forces which are acting on that one object. So, but I will eventually find the presence of that other object via the tension. Right? So again, it's the tension that is the intermediate or the mediating force that connects the two objects together, which tells it that, hey, you're going to accelerate, and then, hey, you're going to accelerate, and this is by the amount at which you're going to accelerate by. Now, the nice thing about Newton's second law is it is very systematic. You do exactly the same thing every time. Start off with a free body diagram, you label all the forces, you choose a coordinate system, you look at the sum of the forces on all the different directions. Sometimes you'll have to use kinematics to find the acceleration. Sometimes you won't have to. You'll just find the acceleration and then plug that into a kinematics. Well, that's it. There's nothing spooky or spectacular or scary about these things. You just do the same thing over and over again. That's it. So Monday, then I'll probably give you guys group assignments, let you work on those for a while, and then from there we'll move on to drag forces. So we'll start talking about drag forces, and then equilibrium, or baby statics as we're going to call it, and then we'll finish off by talking about circular motion again. So we'll look at centripetal forces. We'll talk more about those. But like I said, Monday when we get back, we'll pretty much just be doing group assignments, just getting more practice working groups, trying to figure out how to all these things actually connect together. All right, so I will hopefully see everybody on Monday. Hopefully nothing actually changes. All right.